Now that you know how to prepare and measure your sample, it is time to have a look at the analysis of the resulting data. The first step in this analysis is to find out which phases are present in your sample. This lecture will give you a brief overview on how we identify phases in a so-called qualitative phase analysis on your X-ray powder diffraction data. Qualitative phase analysis is based on a comparison of the peaks in a measured XRD pattern to a large database containing peak patterns of many known phases. Usually, a database such as the powder diffraction file database, the PDF database published by the ICDD, is used, and this database allows searching and matching in combination with chemical or categorical filters to restrict the number of candidates that can match your pattern. Also, open source databases exist, such as the COD database and the American Mineralogist database. As a general help in phase identification, we have supplied you with a list of common phases found in cement, and this is also given as a supplementary material to this course. This list can be used to build a custom database for cement phases for your system, and it can be used in combination with your specific available search match software. Alternatively, there's also the classical way of doing search matching by rapid manual identification by comparison, for instance, between a list of XRD peaks of certain phases and peaks in your pattern. We have also supplied such search match table as a supplemental material to this course, and you can use it to find difficult phases such as minor phases which have very low peaks, for instance. In the graph on the left side, you can see that there's the main problem of identification, which is peak overlap. If you look, for instance, at the overlap between the C3S and the beta C2S patterns, then you can see that the major peaks are actually completely overlapping, which makes it very difficult for any automatic phase identification software to find, for instance, beta C2S in this system. This way, we also need to rely on other information, such as microscopic observations or knowledge of the bulk sample chemistry, or just knowing what kind of phases can be present in your material. Specifically for Portland cements and anhydrous Portland cements, it is very useful to do some selective dissolution to identify minor phases. Having looked at the example in this figure, you can see that for an anhydrous Portland cement, we have done two extractions, two selective dissolutions that either concentrate the calcium silicate-rich phases. This happens with a potassium hydroxide plus sugar extraction in the green curve, or we did an extraction, selective dissolution, with salicylic acid and methanol, in which we have a residue, a solid residue, that is concentrated in the aluminate, ferrite, and alkali sulfate phases. For instance, when comparing the bulk sample in purple below with the SEM extracted sample, you can see that there is a very large increase in the peaks of ferrite and of alkali sulfate phases, for instance ferrite around 12 degrees and alkali sulfate phases in the range of 20 to 25 degrees to theta. As well, this selective dissolution methods can be used to identify whether there's any polymorphs in your sample. For instance, one may really look at whether there's any polymorphs of C2S or there's orthorhombic or cubic C3A in the Portland cement. Finally, the XRD pattern fitting procedures in quantitative phase analysis often indicate the presence in the difference or residual curves of minor or trace phases that were previously hidden by extensive peak overlap with major phases. Therefore, an iterative procedure that goes back and forth between phase identification and phase quantification is very common and very useful in obtaining a complete analysis.
From this session on, we will show you how to do analysis using XRD data. Here are the files we are going to use for the demo. You can find the templates as well as a conversion file and the Mac calculator in Excel files. All the cement-related structures are available as zip files in this folder. The demo will be shown step by step. Part 1 is identification. Part 2 shows simple retrieval analysis. Part 3 will be the advanced quantitative phase analysis. The samples used for the demo videos are simple binary mixture made of calcite and quartz, anhydrous Portland cement, typical SMs including flash and snag, and finally hydrated cement. The demo videos are mainly based on the software called HiScore Plus from Panalytical. A quick demo on how to use the open source software Qualitative for identification and ZSAS2 for quantification will also be covered to enable your own practice in case there is no access to the HiScore Plus. Let's get started with the quantitative analysis. Simple demo using calcite and quartz mixture. Open the HiScore Plus software, then create a new file. Now insert the file. Now insert the data. You can change the scales of the y-axis to linear, square root, or log scale to check the details of the peaks. More details such as the configuration of the diffractometer in the scan can be found in the object inspector. To do the identification, there are 3 steps. First, determine the background of the pattern. Second, search the peaks in the pattern. You can see the peaks on top of the pattern. The black V marks means that the peaks are not identified. Then search match. There are a lot of cards in the database. It is better to know some background information for the sample, such as the category of the sample, for example, inorganic or organic, chemical compositions, crystallography information, and the potential phases in the mixture. The restrictions can be very helpful to improve the search match. We will show all these functions in the coming demos. Here we just search high quality cards using star and indexed. After search match, the candidates are shown in the candidates list. The score indicates how good the candidate matches the experimental pattern. You can check the details of this card by double-clicking the selected cards. We accept the first proposed candidate, the calcite. The remarks are removed for all the matched picks with calcite. After taking the next candidate quartz, most of the peaks are identified. For each phase we picked, it is recommended to check the relative strength match by eye, focusing on the 3 strongest peaks. The remaining tiny peaks are from the K-beta residue. A demo on QuaX2 for identification. Import the diffraction data, then go to search to search match. Pick the candidates from the candidates list. Accept the matched phases. Similar rules to a HiScore Plus will be applied to check the matches of the peak. Make sure all or most of the peaks are matched. Demo on flash and snag. For these 2 demos, we will show the typical patterns for the amorphous humps. As the samples are mainly amorphous with small amount of crystalline phases, it is more challenging to make the decision of the final candidates in the samples if there is no information about the samples. For such kind of samples, the identification must be done with special care by taking as much information as possible, such as the chemical composition. For flash, there are a lot of amorphous content which give us a hump here. For this case, the background function should be modified to follow the hump and just keep the peaks by changing the parameters. The background function should just follow the trend of the lowest points of the pattern, but should not go into the peaks. Let's search peaks. Then search match. We can always pick the star and indexed cards in the identification. With the search match, the best matches was the moonlight followed by quartz. We accept these two candidates for the match by dragging the candidate into the accepted area. However, there is still some tiny peaks which is not unmatched. For example, the peak around 13 degrees. By checking the rest of the candidates, another polymorph of silicon oxide, namely the distrite, matches the peaks. Now all the peaks are identified. For slag, we also see the amorphous hump. The strategy for the background is similar to the one for flash. Follow the lowest points of the pattern, but never go into the peaks. If we search peak quickly, there are only 3 peaks in the pattern. We apply the search match without any restriction. Most of the candidates are quite strange, as the elements are those for sure that existed in the sample. This is mainly because of the relative low concentration of the crystalline phases in this sample. Let's put some restrictions to the search match. For example, the subfile mineral-related cards. Refine the search match, then we got the chords on the top list. When checking the chemical composition of the sample, we know that there are a small amount of silicon oxide in the sample, so the presence of chords is reasonable. Then there are some other strange candidates such as the ice and some rare earth elements compound. The possible candidates would be the calcium carbonates, namely the calcite, according to the chemical composition from XRF. A demo on potent cement. For potent cement, the challenge for identification is from the complexity and similarity of the pattern for C3S and C2S. A lot of peaks are overlapped, which makes the situation more difficult. We do the same steps for data of potent cement, insert a scan, determine the background, then search the peaks. As we know it is cement, so the restriction of cement and hydration products in the subfile is applied. The first candidate is the solid solution for C3S with magnesium and aluminum. The second one is C3S. Both give similar match score, while the C3S matches better when checking the peaks at around 15 degrees. Right-click to accept the candidate. Following is the anhydride. Then is the C4F, namely the brown mineral, if you take a quick look into the details of the card. For the rest of the phases, you can get help from the different types of restrictions to locate. For instance, there might be some free line left in the cement if the centering is not well done. The restrictions based on elements can be used. We pick the calcium and oxygen. In this sample, there is only very small amount of free line. For potent cement, there must be some C2S. As we know, the mineral name of the beta C2S is called nanite. Let's try the restriction using streams. Before we use a lot of restriction, the previous one must be cleared. Indeed, if we apply the restriction based on the mineral name, it will be easier to locate the exact phase. If we just use the element restrictions for the same chemical composition, there are some polymorph which needs to be distinguished. Until now, most of the peaks are identified. There is no C3A found in the candidates list. We put some element restrictions to find the C3A. There is the C3A we need. All the peaks matches the pattern now. A demo on hydrated cement. Now we take a look of the hydrated cement. You can see clearly the hump for CSH around 13 degrees with copper radiation. So the background should be treated similarly to the flash and slag, following the trend of the patterns. As we know it is cement hydrate, so we apply the subfile restriction with cement and hydrate. The suggested matches are A-light. Here it appears as a solid solution of the C3S with some magnesium and aluminum. Then is the potentite, which is the main hydrate for cement. Then you can find the electron which appears as calcium aluminate sulfate hydroxide hydrate. Also check the peaks in the pattern. As the complexity of the hydrated cement, sometimes the software cannot find out the potential candidates easily. Then the restrictions can be used to simplify the search match process. Generally, the C4F reacts slowly during the hydration process. Let's locate this face with the mineral name of bromminerate. The same routine can be used for the C2S, namely nonite. Up to now, all the crystalline faces in the hydrated cement paste was identified. Unsurprisingly, we cannot find the candidates for CSH in the database, as it is nanocrystalline which presented a hump instead of set of peaks. The closest crystalline structure to CSH are the 11 angstrom and 14 angstrom topomorite structure, which is the most used starting structure for model the CSH structure.